Hello everyone, welcome to second tutorial session. So we'll try to see if it can work better than last time. How many of you managed to install things on your local system and able to run it? Okay, so all of you can try to run it on your system and start Jupyter Notebook and set it up. Open tutorial 2 in the tutorial folder. Okay, and how many of you have Windows operating system? Okay, so for all those who have Windows operating system, can you go to this link, which I have already shared, and click on Launch Binder. So only the people who have Windows operating system, because I think otherwise it will be limited by internet. Launch Binder. Once you go there, click on Tutorial folder, and then you'll see Tutorial 2 there, which is again server error. So once you open, click Tutorial and click on Tutorial 2. Now everyone else, can you try connecting through SSH? So for that, you have to open a terminal. And type this command, which is shown on the left side of the terminal. Okay, so you have to open terminal, type this, and it will ask for password. The password is same what I shared last time, which is Cosmology 20K19. Once you have done that, once you have typed the password, press the enter, then open this website, which is the link is given on the right, on any browser. And that will again ask for password, which is again Cosmology 20K19. So can people connect? Through SSH? Anyone able to connect successfully through SSH? Here. So are you not able to type the password? At what level you're stuck? Yes? Sorry? Sure. Yeah, so that's the command. It should be already there in your Slack channel, which I shared last time. You can also copy paste. So people who are not able to connect and having problem, please raise your hand, and everyone else who have connected, can you please try to help each other? So let's see how many are able to have working Jupyter Notebook now. Can you raise your hand? Okay, so that's most of you. Whoever haven't got working notebook, can you work with your neighbor for now? Okay, so sorry, it always takes a long time to set things up. But now, so in this session, we are going to work with a simulated galaxy catalog and see how to measure clustering for that. So you have already seen most of these things like basic background. For example, Stefano talked a lot about n-body cosmological simulation. What is really n-body cosmological simulation? I just want to show you a video, very quick video. So what shows is like if you start with n-body simulation with initial condition of particles and you evolve them, then how does it look like? So the particles are going to interact with each other and finally collapse, and they will form highly dense region. Those are halos. So halos are basically strong clumps of dark matter particles, and those halos are going to interact with each other and form the whole cosmic web. So all the green region is a high density region which is full of halos, and you can see cosmic web structure in that. So as you go to higher and higher redshift, you'll form more and more nonlinear structure. So the next question comes in, if you want to work with galaxy sample, then how does galaxy live in dark matter halo? How do you figure out where should galaxy be? And we use it, we do it through HOD for the time being, but there are several other methods like sham as well. I'm not going to go in detail of any of those things because the main purpose is to actually do the measurement, but to give you an idea, the question you ask is how galaxies populate this halo distribution. So in n-body simulation, you can find halos. You have halos in the box. So the way you work with the idea that each halo will have central and satellite galaxies. So any halo can have either 1 or 0 central, because at same position you cannot have two different galaxies. Depending on the galaxy population, you ask what should be the number of galaxy as a function of halo mass. General idea is in a massive halo, you'll have more galaxy. In less massive halo, you'll have less galaxies. And then you again ask like what should be the functional form for the satellite galaxy. How many galaxies you should have as a function of halo mass in a given halo. Once you have this functional form, which you construct from data and semi-empirical models, you go to your n-body simulation, which I showed you, go to each halo and populate. Basically, put galaxies by hand according to your numbers you have derived. So that's essentially HOD. Now, once you have this, what you'll have is three-dimensional position and velocities of all of these galaxies. So I've generated a file for you which contains a catalog created in this manner. So the first 3 columns in the file are X, Y, and Z position of these galaxies. What we want to do is we want to measure clustering for this. So we want to measure correlation function. I've already introduced, and several people have talked about it, how is correlation function defined in measurement. So you want to do this pair count, which is what I talked about last time, of galaxies as a function of distance. So that's dd of r, and you want to compare that with a random distribution. So you create a random catalog, which is basically throwing random points in a box, and you count RR, number of pair of randoms as a function of distance, and you construct this quantity, which is correlation function. And another way to write it is this way. They are basically equivalent, but they are different in noise. So in data analysis, we normally use this because that has better noise property. So now you have to understand the idea, which is all of this is in 3D. We have been only talking about as a function of R, which is coming from basically homogeneity of the universe, homogeneity and asymptotropy of the universe. So once you know the pair separation, that determines correlation function. But let's say if you are interested in looking at how the correlation function will look like if you decompose distances. You don't just talk about R, but you also talk about angles. So in observation, one of the things you have to worry about is what is your line of sight. So each galaxy you look at, it can have different line of sight. So when you're looking at a pair of galaxies, so in this picture, what I'm showing is this bending of space is because of dark matter halo, you cannot see that. And at the center of that, galaxies are living. So I want to count a pair of galaxies, but I want to decompose distance between these galaxies in 2 parts. One is parallel to the line of sight, one is perpendicular to the line of sight. So I will measure correlation function now as a function of these 2 distances, parallel to the line of sight and perpendicular to the line of sight. So this is what our first task is, to measure this. And in equation, if I will write that, now I will write each of my pair count as a function of r perpendicular and r parallel. So these are 2 distance along 2 different directions, right? So I want to do all of this pair count as a function of this. There are a lot of public codes which you can actually search and easily download and find. If you understand the ideas and decisions you have to make, you can use any of these codes. You don't really need to understand the details of how it is measured, but you need to understand what decisions you have to make when you run this code. So the first thing is the file which contains this data I just described about Galaxy Catalog is at this location. So this is the name of the file. So you have to use that at some point. And now to measure this clustering, I'm going to tell you this function which I have defined. You don't need to understand how this function works. You just have to understand the signature of the function. In Python, so I think this is something I didn't mention. In Python, you can write a function, declare a function just by saying def, and then function name, for example, get z, and you'll have some inputs. For example, data file here, And then let's say you can have input which will look like something like this. And then you can have much more thing. So this is just saying it's a function. So to call this function, you just have to call this name. And this is the input you must provide. So if you don't provide this input, it won't run. It will give you error. And for now, this input is that data file. So you have to provide the data file. And any input of this kind, which is like something equals to something, that's an optional input. You don't have to provide it. You can ignore it for now. So these are the default value, whatever is written there. So I'm going to discuss slowly like only few things about it. And as we progress, I will discuss more details about this function. And then it will return something. So the function will return something. So let's say if I want to call this function, I will say, okay, my output, my z. And these are just variable name. You can have anything, any combination of letters for that, equals to get z and my data file, plus if you want to give any optional input. So this is how you call function in Python in general, right? So this is the function we are going to use, getZ, which measures correlation function. And the first input is file name, which is this. So this is your file name. And let's say we don't talk about all the other details for now. And it returns a dictionary. So let's just look at some of the inputs of the function. So the one of the input is rlim. So what is rlim? If you want to measure any correlation function, last time I told you the first thing you have to think about is what are the scales you want to measure it up to. So I told you like you have to think about what is the minimum length scale, what is the maximum length scale, and how many bins you want to create. Right? Now we want to do it in 2D. So there are two axes, r parallel and r perpendicular. So what rlim takes is what is the minimum value of r perpendicular, what is the maximum value, and then again same for r parallel, minimum and maximum. Remember, during any of these exercises, never give a value more than 30. Never give a maximum value more than 30, otherwise it will run forever. So all the running time is going to scale with 30, and we want quick results. So we just want to understand the structure. If you give large number, it will take hours to run. So it will just be sitting there. The next is n bins. That's another input. And this just tells you between rmin and rmax how many bins you want to create. So that comes from understanding of what kind of feature you want to look. I will suggest you create roughly a bin size of 1 megaparsec. So let's say if you give 0 to 30, you use 30 bins. And so this is bin around r perpendicular, this is around r perpendicular, r parallel. And the last thing is L box, which is the size of the simulation box, which is 250 now. So this is again a fixed input. So you have to essentially make a call where you want to measure this 2-point correlation function and make a decision about these things, and finally make a plot of it. So let's talk a little bit about what it returns, and I don't want to show you solutions. Yeah. So what does it return? Like once you make a call like this, what will it return? It will return a dictionary. So in Python, dictionary is essentially, it's a set of variables inside one variable where you just label it. So if you want to see what are the things it's returning, you just type, let's say, if your call is myz, you say myz dot keys. It will tell you what are the things it has returned you. But the main thing you are interested in is the correlation function. So you are interested in correlation function. So it will return something called Z2D. Right? What Z2D is going to be a matrix, a two-dimensional matrix, where one axis is r perpendicular, other is r parallel, and it will just contain the value of correlation function at each of these points. So you'll get a matrix. Now you want to plot it. So in Python, to plot a matrix like that, you just have to do pl dot imshow and then your matrix. So right. So if you just type this command, it will make a plot of your matrix, and then you can add a lot of Oh, you can't see this. Did I type that in the? Yeah, so those commands are actually typed in the notebook as well. But let me just write a little bigger. So you want to pl.imshow and then whatever your matrix is. So you just type this and it will make a plot of it. So if you understand the signature and you understand what should be the output, I just want you to give it a try, take 10 minutes time. And if you have completed the task, then just try to help your neighbor, whoever is struggling. If you're struggling, then just raise your hand. So you have 10 minutes to give it a try. And if you have a question, just raise your hand about it. So I'll just repeat once more. I want you to measure the correlation function, load from the data file which is written there in the notebook, and make a plot of it. You also need to worry about if you want to see certain structure, what quantity should you plot? Should you plot correlation function? Should you plot logarithm of correlation function? And things like that, so that you can just give it a try and see what you get. If you are lost and you have question, just raise your hand. I will come to one of you. And you have 10 minutes. Okay. Yeah, so to plot the, I've plotted a circle just for comparison. So this is the isotropic. So what you're seeing is everything is isotropic, which is what we started with. And in n-body simulation, you can clearly see that. But there are all these wiggles around it in these isotropic contours, which is nothing but noise, because we have limited number of galaxies, and all of this is going to have noise. For example, the first noise is going to be short noise. You're counting pairs, so you're going to have short noise in there. So this is noisy, but it's going to be symmetric, right? But what will happen if I were to do this in redshift space? If I will move these galaxies in redshift space, because that is where we observe. So the difference it's going to have is something like you have x, y, you have x, y, and z, all positions. But let's say we consider one of them is line of sight axis, right? This is what we assumed with. So given we are working with simulation, let's say we consider the z axis is our line of sight. So if I want to mimic real observation, what I'm going to see is that I'm not going to see this true z of these things. So all of these galaxies is going to have a velocity along z axis. So that velocity is going to be added to your line of sight distance. So if you add that line of sight distance, then that is what you're going to observe. And how do you construct it? So z, let's say z RSD is equals to z real, actual z, plus you'll take peculiar velocity along z axis and scale it by Hubble constant. If everything is in co-moving distance, then in place of true redshift, you'll measure this. So if I will go and move all of my galaxies to redshift space, then I will measure clustering again. Then what I should see is that I should see redshift space correlation function. So I won't see isotropic correlation function. This is why we started measuring it as a function of r parallel and r perpendicular, because we want to see this anisotropy, right? So to do this, for anyone who actually successfully completed this, all you have to do is just rerun whatever code you have written, but say that RSD, there's a variable RSD. So there's an input to the function, which is RSD. Since it's a simulation, I know the velocity. I can't do this for real data, but I know velocity for everything. So you just have to say RSD equals to 1. By default, it is 0. So in your function call, the new thing you add is, you say RSD equals to 1 now. When you'll do that, what it's going to do is going to move these things to its redshift space, and then you remeasure your correlation function, and then again make the same plot. Okay, so for people who have done the first step successfully, try to do this. And for everyone else who is still trying to do the first step, you still try to do the first step. I'll again give you 10 minutes. And if you successfully do the first step, second step will be very easy. You just write the same code and say RSD equals to 1. Okay, so I'm going to give you 10 minutes, and then also anyone who are able to finish this quickly, please try to help with this. So this is the last thing we want to do today. If we can make a successful redshift space correlation function plot, we have learned how to measure clustering in a simulation box. So you have done this pl.im show whatever my z 2d, something like that, right? To take log of that, all you need to do is replace this by, so numpy has a log function, log 10 my z. You replace this there, and then it will plot log of the same thing. So your 10 minutes is over now. People could do redshift space correlation function I have a plot of it. Can you raise your hand, like, so that I can see? Okay. So about 20%. So rest of you either come to me after the session if you have difficulties, or you try to do it on your own time. So this is, so are you able to see something which you have seen in several talks? Are you able to see a plot which is something you have seen in several talks, right? So you've got something like this, which looks something like this. So again, now what you can see is that if I compare that with circle, there is a large scale Kazarian fall, and at small scale you see finger of God effect. So you already know all the physics behind it, but you can actually see this in simulation, and you can do similar analysis for data. So now we are almost done. I will just tell you one more idea, and I'll give you a task which you should do later. So now that we have made a plot like this, so in several talks you heard about multipoles, monopole and quadrupole. That's how we measure correlation function. So what are these multipoles? A little bit more at the practical level. So this is what you measured. That's R perpendicular and that's R parallel. This is your correlation function. Now you want to extract signal out of it. So right now you have a lot of points with a lot of noise. So whenever you want to do analysis, you also have to characterize noise. So you want to simplify this. You don't want to like work with R parallel, R perpendicular, and so many values of correlation function in each bin. So you want to simplify it, and at the also model level, it makes sense to look at multiple expansion of this thing. So this is a very generic idea which you might have come across in your undergraduate degree, which is legendary polynomials. So if this was a circular pattern, isotropic pattern, then what do you expect is that it's isotropic, so only monopole is non-zero. Any higher order multiple moment is going to be zero. But given that RSD is going to create this distortion, we should be able to measure monopole and non-zero quadrupole moment. So the way you do it, you take your correlation function, you just integrate it with mu, a function of mu, which is as shown here. Now, anyone heard about PL equals to 1 mode, or have seen plots PL equals to 1 in any of the talk? Do you remember seeing dipole moment in any of the plot? Do you know why? Why people never talked about dipole moment when they show galaxy clustering? Because there is? So this has nothing to do with mass itself. This is a movement of this pattern, right? So the reason why they didn't talk about dipole moment, there are effects actually which could produce dipole moment, but for now, whatever we have studied, the line of sight, where when you look away from the observer versus towards the observer, it's symmetric. So there is no difference between the two, as long as you take care of your selection function of the survey properly. So what you expect is that this is mirror image of that. In fact, that's how you're constructing this plot. So given that the point on the top versus point on the bottom, which is a mirror image, like reflection along x-axis, it's going to be mirror image. If it's mirror image, then this function moment is going to be 0. So your dipole moment is 0, which is why nobody talks about it in standard galaxy clustering. So this is going to be 0, and so you can look at monopole and quadrupole moment. Now, if you want to do it with like the set of codes, this function, then let me just describe you how to do that, and you should do it afterwards. So slowly you're understanding inputs of this function, right? Now I've described, you have already used R limit, you have used NBin, you have used LBox, you have used RSD. Now there's something called Samp Mode, right? So when you want to work with these things, you have to make a decision about what sort of sampling you want to do. So in fact, what you can do is that the correlation function you have measured, you can already interpolate it and integrate it. It's a simple integration, but you need to interpolate it. But what you have been doing now, you have been creating bins like this. So you're sampling in R perpendicular at certain bins, R parallel at certain bins. And now you can do this integration along theta, but you have to interpolate things in properly. You have to make sure, okay, this bin have only certain fraction of that in your radial bin and things like that. But alternative choice will be, so this is your R perpendicular and R parallel. What I will do is that I will make radial bins. So I will split in theta and I will split in radius. To start with, I can make this choice and I can measure correlation function in place of r and theta. So that's polar coordinate. That will be easier to integrate to do monopole. So to do multipole, you just have to sum things as long as you have fine enough binning by multiplication factor. So to do this, all you have to do is change Samp mode. So Samp mode default value is 1, which is do Cartesian binning. If you change that to Samp mode equals to 0, that will do that angular binning. But then that will also mean your R limit will mean different things now. So R limit, this was R parallel mean, R perpendicular mean, R perpendicular max, and R parallel mean max. So now you're doing R theta bin. So the first coordinate is R. So now you have to give the bin limits of R. And the second coordinate is not theta, but what we call mu. So mu is nothing but cosine of theta. So let's say this is your line of sight. The angle, this is theta, and you can convert that mu equals to cosine of theta, because that's the space in which legendary polynomial is written. So this will be mu equals to 0, and this will be mu equals to 1. So the second axis will be range of mu. So these numbers should change accordingly. And then you have to give the number of bins different. So you have to do a few things. You have to change Samp mode to 0 so that you do R theta sampling. You have to change the limits of your binning, and you have to change number of bins. Once you change these two things, what this will give you is multiple moments essentially. So you're able to do this Z2D. So similarly, it will print something called Z0, your dictionary, and then it will have Z2. So these are monopole and quadrupole. So I'd like you to run with these changes and make a plot of monopole and quadrupole and see if it looks something similar to what you have seen in these talks. Right? So yeah, I will stop here for this session. If you have any quick question, you can ask me now or we can discuss later. Okay.